Previously, we qualitatively analyzed the working principle of the common emitter amplifier circuit. When we design an amplifier circuit, we need to understand its performance indicators, so we need to conduct a quantitative analysis of it. The performance indicators of a circuit mainly consist of static and dynamic indicators. First, let's analyze the static indicators of the amplifier circuit. Design a reasonable static point. The teaching objectives of this section are: 1. To analyze the static working point of the amplifier circuit using the estimation method and graphical method. 2. Adjust and measure the static working point of the amplifier circuit. The common emitter amplifier circuit diagram. When the inputs equal 0, the amplifier circuit operates in a direct current state, also known as static. Static analysis is when the input signal is 0, to determine the static values of the amplifier circuit. At this time, the base current, IB, the collector current, IC, and the voltage, UC, between the collector and the emitter, are represented by an IBQ, ICQ, and UCQ. The working point determined on the characteristic curve of the transistor is called the static working point, represented by Q, the Q point of the transistor, whether it is in a suitable position on its volt ampere characteristic curve. This is a prerequisite for the amplifier to normally amplify the signal. Analysis include the estimation method and the graphical method. Static analysis is when the alternative current input signal 0. All signals in the circuit as time are direct current signals, so we only need to analyze the direct current path. When drawn the direct current equivalent circuit, capacitors in the circuit can be considered as open circuits. Inductance can be considered as short circuits. The internal resistance of the power supply is neglected. The direct current path is shown in the figure. Let's first look at estimation method for the static working point. Calculate as follows according to the direct current path. UCC equals IBQ, RB plus UBE. IBQ equals UCC minus UBE divided by RB. When UCC much greater than UBE, IBQ approximately equals UCC divided by RB. For silicon transistors, it is 0. 7V for germanium transistors, it is 0. 3V we can also use the output characteristic curves of the transistor to find the static working point. That is, graphically finding the Q point. 1. Write out the direct current load equation. UC equals UCC minus ICRC. Determine point M on the horizontal axis. UC equals UCC, IC equals 0. And determine point N on the vertical axis. UC equals 0, IC equals UCC divided by RC. Connect points M and N to draw the direct current load line. IBQ equals UCC minus UBE divided by RB. From IBQ equals UCC minus UBE divided by RB. Determine IBQ. Find this curve. An intersection with the direct current load line is the Q point. Read the coordinates of the Q point, IBQ, ICQ, and UCQ, which is the Q point we are looking for. The so-called distortion refers to the output waveform of the amplifier not being proportional to each point of the input waveform. The main cause of distortion is the Q point position of the transistor is not appropriate, causing the working range of the amplifier circuit to exceed the linear range on the characteristic curve of the transistor. This kind of distortion is called a nonlinear distortion. In order to obtain as large an output signal as possible, the Q should be set in the middle part of the alternative current load line. If Q is set inappropriately, the signal enters the cutoff region or the saturation region. It will cause nonlinear distortion. As shown in the figure, a static working point is set in the middle part of the alternative current load line. The input signal works in the amplification region. Output signal is completely distortion-free, as shown in the figure. Here, the static working point is set to low. The input signal enters the cutoff region. The output signal undergoes cutoff distortion. As shown in the figure, the static working point current sets to high. The input signal enters the saturation region. Output signal undergoes saturation distortion. We have conducted a static analysis of the transistor amplifier circuit. For the amplifier circuit, a suitable static working point must be selected. The static working point is generally chosen in the middle of the transistor's output characteristic curve. Let's conduct an experiment next. Adjustment and measurement of the static working point. The experimental circuit schematic is shown in the figure. Input a 20 mV sine signal with a frequency of 1 kHz. Adjust the potentity at MRP. Observe the output waveform without distortion using an oscilloscope. Measure the static working point at this time. Record the experimental data. Now on the experimental platform, carry out the adjustment and measurement experiment of the static working point. Insert the circuit board into the test bench. Connect the circuit according to the schematic on the experimental circuit board. That is, connect holes 3 and 5 with a wire. Connect holes 4 and 5. Connect holes 5 and 6. Connect holes 7 and 8. Connect holes 9 and 10. Connect holes 10 and 11. Connect the signal generator at holes 1 and 2. Connect the oscilloscope at holes 12 and 2. After checking for errors, connect to a 12V direct current power supply. Adjust the frequency of the signal generator to 1 kHz, a sine wave signal with an amplitude of 20 mV. Add it to the input end of the circuit. Use the oscilloscope to observe the waveform of the output voltage. Adjust the potentity at MRP so that the output voltage waveform on the oscilloscope is not distorted. Then turn off the power of the signal generator. Measure with a digital direct current voltmeter. Measured UBV3, 49V voltage from hole 9 to ground. Measured UF2, 88V. USP is about 288V. This connect hole 7 and didn't connect to a digital direct current ammeter. Measure ICMA about 195 mA record in the table. After the measurement is completed, calculate the theoretical value and compare it with the measured value. In this class, we analyze the static situation of the amplifier circuit. The next class will conduct dynamic analysis. The content of this class ends here. Goodbye, classmates.